Well, I want to talk about tipping and slipping in dynamics today. This is actually part of Chapter 17, the translation section. However, I wanted to talk about it in a separate video because it is slightly different from any other technique. There's a couple of twists in here that are different from techniques that we use in any other section. So first, let's refresh our memory about tipping and slipping in statics. So again, if in a static condition we know that it slips if the force of pushing, the P here, exceeds the force of friction. Force of friction is maximum when it is equal to mu normal. Therefore, if P is greater than mu normal, or P is greater than the force of friction, we can say that it is slipping. The tipping condition comes from you recognize whether or not about what point it's going to tip. And in this case, if I'm pushing on this side, it would tip about point B over here. So what I just do is sum the moments about the tipping point, and when I do that, I notice that, and when it does tip, we notice that the reaction at A, or the normal force at A, goes to 0. So all I need is the tipping condition would be if the moment to tip is greater than the moment to restore. So the moment to tip would be P times H going in this direction. The moment to restore would be mg times this distance, and we'd say that if that tipping moment is greater than the restoring moment, it is in tipping condition. The other way of doing this is in our statics book we talked about setting up a pseudo distance through which the normal force acts, and we can evaluate the tipping condition by summing the moments about g. Alright, so what we're going to do here is, if we sum the forces in the x direction, it is not in a slipping condition, so therefore P and some of the forces in the x, so that says P and a force of friction have to be equal to each other. So then if I sum the moments about g, I have P times the difference here, h minus y, going in that direction. I have mg goes through g, so it doesn't matter. The force of friction here has this distance y going in that direction, so that's also in the same direction as P times h. And then we have the normal force acting through a distance d away from the center of gravity. And what we're going to do is analyze this, sum the moments about g, and if the d distance here is within this distance, we can say that it is in a stable condition, and that is not tipping. If the distance d that we solve for is greater than x2, or if it lies out here in space someplace, we see that that is a condition that cannot exist, therefore it is tipping. Alright, so again, that's a somewhat useful method as well. A couple other things about tipping in statics. We noticed that in statics that the center of gravity and the location of the pushing force did not help us determine whether it was in a slip condition or not. So it doesn't matter where P is located, if it's pushing on the box, or where CG is located in the y direction. Slip condition does not depend on either of those. And there was also no provision for a tip over backwards scenario. Whereas if you're pushing down here, you got a center of gravity up here, you push here, you know it's probably going to tip over backwards, but we could not analyze that in statics because slip would always occur first, and we have to analyze that condition first. Alright, so in dynamics, we have quite a few more options and more things that could happen. So in other words, in dynamics it can either slip or tip, or neither or both, and we need to analyze all of those conditions to figure out what's going on. There are two basic types of tip-slip scenarios we want to visit about. One is with the pushing force like we have on a flat surface, and the other one is where a box or some object is sitting on a cart, and we're going to pull it and we're going to see whether it slides off the back or tips over the back. Alright, so first of all, let's analyze this scenario here with the pushing force in dynamics. So again, to find out if it's slipping, we can either use statics or we can use the dynamics equation. Some of the forces in the x is mass times acceleration in the x. And if it's slipping, force of friction is mu normal. And so some of the forces in the x, we got P minus force of friction would be mu normal. And that's going to be equal to our mass times acceleration in the x direction. And we find that the slip condition is identified. If ag is less than 0, then it's not slipping. If ag is greater than 0, then it is slipping. The tipping condition is also relatively straightforward. What we noticed when it tips is that again A would go to 0, and it would probably tip. It would tip over about point B. So summing moments about point B would be a convenient place. And we first, to analyze tipping, we if it is already slipping, then the force of friction is equal to mu normal. If it's not slipping, then we're back to statics anyway, and we're just trying to use one of those other methods to evaluate tipping. So in order to evaluate in dynamics, we're going to assume basically that it is in the dynamic situations, therefore it is slipping already, and then the force of friction is equal to mu normal. All right, so again, some of the moments about B would be convenient. So we're going to say P times H going in this direction. And we have mg going in this direction. So let's see, our positive direction, let's make that counterclockwise. So that would be negative P times H going in that direction. We have A going in that direction as well, and that's going to be x1 plus x2 as my lever arm, minus mg times x2, that lever arm, and that's going to be equal to my mass times acceleration vector going in this direction times its lever arm of y. And again, the mass times acceleration vector is going in the clockwise direction, so it's negative as well. We can also use some of the forces in the x direction, and we see that P minus mu normal is equal to max. We have two equations, two unknown situation. If it's in tipping, A has gone to 0, so this term has gone away. It's nice to leave it in there in our scenario for adding things up, because in some cases we may be saying what are the normal forces given a certain P. If we're looking for the P to cause it to tip over, then again A goes to 0, and we're just looking for trying to resolve this two equations, two unknown situation for P and A, and we can do that. All right. And again, like I just said, for a given P, you can also find the normal forces, and then you'd leave that force A in the equation. The other thing that we can do is use the other evaluation method to find out whether it's in a tipping condition, and we can sum the moments about G, and we can say sum of the moments about G is equal to 0. Again, when G goes through 0, or when we're summing moments about G, mass times acceleration vector goes through G, mg goes through G, and so the only thing we'd have is P times this lever arm here of h minus y. Then that goes in that direction. Then we'd have the force of friction. Again, it's in a slipping condition. And so that means force of friction is equal to mu normal. That's going in the clockwise direction as well. And then going in the positive or counterclockwise direction, we'd have normal force times that distance d. And again, if d is within our bounds of our object, when we solve that, then it's going to be stable and not tipping. If d is greater than x2, or d is out here in some place, then it would be tipping. All right. So this method, I just want to note here that this method can evaluate a tipping condition for a given P. However, it does not help us evaluate the P required to tip. In other words, if we were to say what P is it going to take to tip it over, we have to go back to the other method in order to do that. So this is useful to evaluate a tipping condition with a given P. All right, here's an example. Let's go through real quick. Let's say that we have a 4 kilogram box with a mu with the ground of 0.01. We want to find out, and here's some dimensions. We're going to push P at 2 meters above the ground. We have the mg 1.5, and then the box is a little off center here. G is 0.5 from this side and 1.0 from that side. So to evaluate slip, some of the forces in the x is mass times acceleration in the x. Again, just to evaluate the slipping condition, we find out that it takes 3.924 newtons. That's the statics analysis. And then at that point, is it tipping? Again, we're back to statics, and we can say that if A has a normal force, then we can say that it is not tipping. So I can say that some of the moments about B is equal to 0, and I can say that A is equal to 20.93, so it's not tipping. Now, we may also say, though, we know what P is required to make it slip, because that was given there, but what P is required to make it tip. And here's where we set up the dynamics equation. Again, we're going to sum moments about B. We have P times 2.0. we have mg coming this way times 1.0. If everything is about point B, a goes to 0, and then we have to have our mass times acceleration vector in there times its y bar. Setting that up, we can solve this two equations, two unknowns situation. We have to have some of the forces in the x is mass times acceleration in the x, and you can see how I solve that. Some of the moments about B, and we get these two equations, and we can see that it takes a 66 Newton force, and it will be traveling, or it'll be accelerating at a 15.7 meters per second squared acceleration in order for it to tip over. Well, the second type of scenario we want to talk about is where we have a box sitting on a cart and we're going to yank the cart that way. The box may slip this way or maybe tip over backward, and we want to find out what conditions will cause that. A similar kind of thing is where you may have a box on a conveyor belt, and we're going to give that some torque around the motor here, and it's going to cause some acceleration. And again, we want to find out if it slips backwards or if it tips over backwards. Okay, so to analyze this slipping condition, we carefully draw a free body diagram, and we recognize that the only thing pushing the box forward is the force of friction. And there are no other x forces on here, so we can sum our forces in the x as mass times acceleration in the x. We know that for slip to occur, the force of friction is equal to the slipping condition, which would be mu normal. And so I can plug that into here, and in this case it's mu mg because everything is going in the vertical, all the forces here, vertical forces are on a flat. So I can say the force of friction is mu mg, that's going to be equal to max. So we can find out the acceleration required to slip is equal to mu g. What we see that is that if the acceleration that we're trying to accelerate this thing is anything less than mu g, it won't slip. If we try to accelerate it greater than mu g, then it is slipping condition occurs. Now again, we can never have a greater acceleration than mu g. This is acceleration maximum from slipping. It can be less than that, but it cannot be more than mu g. The tipping condition, very similar. We draw a free body diagram. In this case, we notice that if it tips over backwards, the force of friction, the normal force at B goes to 0. So we can move the normal force back here to this contact point. The force of friction is there. And we can now sum the moments about A or G or any point really. It's convenient to sum it about here because that way the force of friction goes through A and normal force goes through A. And to evaluate tipping, we just say that the sum of the moments about A is equal to our mass times acceleration in the x direction times y bar, which is right here. And so if I say that's my positive direction, this is positive, I got mg times this distance, x1, is in the positive direction, that it's negative, and that's going to be equal to my mass times acceleration vector times its lever arm. But again, that's going in that direction, which is negative, so I have minus mg times x1 is equal to minus ma times y, and I can see the acceleration of g, the center of gravity, is equal to gravity times the ratio of these distances. Now again, you cannot accelerate any faster than this without it tipping over. Obviously you can accelerate less and it won't tip over. So we're looking at the maximum condition here. Alright, so here's an example of this. We have a cart that has a mass of 5 kilograms, a box that weighs 4 kilograms. We're going to push on it with some force, and we want to find out the maximum P so that it will neither slip nor tip. So to evaluate, again, the acceleration for the slipping condition, we do it just like we did before, and I can find out that it takes 0.981 meters per second squared to slip it. If we find out the acceleration required to tip, do it just like we did before. Again, the normal force goes over here. We've got at that moment trying to restore, and it's going to be mass times acceleration times 1.5. We can see that AG has to exceed 3.24 meters per second squared in order for it to tip over backwards. So then, in order to find out which one rules, we pick the lowest one. We say, okay, it cannot exceed this one without slipping, and it's never going to get to here because it slips first. In this case, if it says the maximum P so that no slip or tip occurs, then this one would rule. So then we just look at our assembly then. We're going to say that P cosine 30 is going to be equal to our total mass times acceleration. And we can see that P is equal to 10.19 newtons in order to make it slip. Now the last piece I wanted to visit with you about is inclined planes. And both of these conditions are easily managed on inclined planes, and it's really not very hard. All you have to do is keep track of our mg sine theta and our mg cosine theta. So what we generally do if we're pushing a box up a hill, in order to analyze the p required to slip, we say the sum of the forces in the x. I guess I didn't write that down. The sum of the forces in the x is equal to mass times acceleration in the x. And if we're trying to find the p required to just barely slip, then magx is going to be equal to 0. So we can solve p minus mg sine theta minus the force of friction. In this case, force of friction is going to be mu mg cosine theta, and we'll solve that for p. The p required to tip, very similar again. It's going to tip over point B. A will go to 0, so we'll have all those going in this direction. So I'll say some of the moments about B is equal to the mass times acceleration times my y bar. So I got P times H. That'll go in the clockwise, so that's negative. Then I got mg sine theta times y. Let's see, that's going to be in the positive direction, going that way. Mg cosine theta. It's going to be that component, and that's times my x2 right there, and that's going to be positive. And that will be equal to magx times y bar. Now that vector is going in that direction, which is going to be negative, and so we can solve this for. Well, actually, we can't solve this for anything yet because we don't know the p required and we don't know the acceleration. So we're going to have to do a sum of the forces in the x direction. And we can see that p minus mg sine theta minus mu mg cosine theta is equal to magx. Two equations, two unknowns, and we can solve for both p and a. And so the second scenario would be if we have a cart and we're pulling it up a hill and we want to find out what force here, what p would, what our maximum p is in order to keep it from either sliding backwards or tipping over backwards. So again, we draw a free body diagram of just the box and we analyze our acceleration for slipping and our acceleration for tipping. And in order to do that, we can sum our forces in the x direction. Again, I've got an mg sine theta going down the hill, I got a force of friction going up the hill, and that's going to be equal to my mass times acceleration. And force of friction here would be equal to mu mg cosine theta because it is slipping. I can solve for the acceleration required to make it slip. And then the tipping condition, if it tips over backwards, it would rotate about point A, so that means the normal force moves to here, force of friction goes through there, B goes to 0, so I would have my sum of the moments about A is equal to my mass times acceleration times y bar vector, and I got mg sine theta times my y going in that direction, which would be positive, mg cosine theta times x1, which would be going in the negative direction, and that would be equal to my mass times acceleration vector times y going in the clockwise or negative direction. Anyway, I can solve this for A, and I can obviously have solved this one for A. I compare the A's and see which one rules. The smallest acceleration would be the most we could stand before it either slips or tips. Once I find the acceleration, then I can go back to this scenario and say sum of the forces in the x is equal to mass times acceleration x. Taking the mass of both the cart and the box into account, I can find out what the maximum p would be.